Hello. Hi. Thank you so much to the organizers for the invitation. I'm deeply honored to be here and be able to tell you about our work. And also, I did get some time to go around Taipei, and I definitely agree it's a very beautiful city. I'm going to tell you today about our recent error correction experiments that we've been doing with neutral atom quantum computers. This was done in our Harvard lab that was, yeah. And then, yeah, I'll tell you about our results now. I've never given a talk in such a large conference hall. So, okay, so I am an experimentalist, at least primarily, and I'm going to tell you, so to start, about various frontiers of experimental quantum information science from the past few decades. So, in the 2010s, there was really many very beautiful early experiments done, also extending a little bit before this, starting to explore small-scale quantum computation with physical qubits, and we kind of started to learn a lot about what does quantum computing look like, and what do quantum algorithms look like, and how does implementing them look like. And recently, we've become better and better at controlling these physical qubit systems, now to the level that we can assemble these systems into complex many-body systems that start to do interesting things and start to really try to use this as a scientific tool to make quantum discoveries. This is one kind of big thrust that's pretty exciting right now in experimental quantum information. And another one is that of the error correction frontier, and that's going to be the focus of today's talk. And what this means is that we can take our physical qubits and then combine them into conglomerate logical qubits. And just very recently, and quite amazing milestone demonstrations, people have been able to do kind of the first one or two logical qubits and gates in these various systems. And that's going to be the focus of today's talk. And broadly, in our path toward trying to build large-scale quantum computers, the central challenge that we are fighting is that of decoherence and trying to figure out how to manage decoherence in large-scale quantum systems. And currently, to date, quantum error correction is the only known realistic route that we have in order to suppress gate errors down to those that are required for algorithmically relevant problems, where we have, for example, our physical qubits have errors on the scale of 10 to the minus 3 per gate, and we need to get to below something on the scale of 10 to the minus 10. And actually, before quantum error correction was invented, people thought that quantum computing would actually just be fundamentally impossible, that you wouldn't really be able to benefit from quantum computers. And it's quite remarkable from a fundamental perspective that quantum error correction is actually even physically possible. The common classical error correction example, which works in a quite simple way, is that of copying information, where you can just take a single bit that you care about and then, for example, copy it 3 times. And now if a single bit fails, you'll be able to detect that that was the bit that failed and do majority voting. But there's a variety of conceptual challenges trying to apply this kind of phenomena to quantum error correction. So one is that we can't copy quantum information. There's this infamous no cloning theorem. And another is that, if you want to check for errors, you have to wonder how to do that without actually measuring the qubit and collapsing its state. So for these two reasons, people actually, had originally thought that quantum error correction was not even physically possible. And due to kind of really breakthrough theoretical work in the 90s, people found that you can do quantum error correction with this ingenious concept of entanglement, which is that you can use entanglement to take a logical qubit that you care about and then spread it out and delocalize it across many individual physical qubits. And this non-local spreading will now encode a logical qubit, where now this logical qubit is so delocalized that it actually becomes hard for the environment to accidentally manipulate. And it turns out that actually we can measure products of qubits, these are our checks or stabilizers, in order to detect errors while preserving the quantum information and not projecting the underlying state. And a classic example of this is that of the toric code invented by Kitaev in '97. And it's given here by a lattice of qubits here with periodic boundary conditions on a torus. And there are these X and Z check stabilizers, which are these 4-body products. And the ground state of the toric code is given by this error-free state where all of the X and Z products, all these stabilizers, are equal to +1. They're all these mutually commuting 4-body operators. And then we can just, from this state, just directly read off the logical qubit by looking at these logical X and Z strings, which are products of X's and Z's that run vertically and horizontally across the lattice. And what happens now is that a physical qubit error, for example, on this qubit here, will cause these local checks, like for example these z checks here, to show that an error happened at a specific location, and we can now infer that this error happened, and which we call decoding, this inference process, and then undo this error. And as our lattice size increases, or our code distance, d, here given by our lattice size, increases, we do get more opportunities for errors, but we also get more checks. And this gives us a kind of threshold behavior, where if we're below some kind of characteristic threshold error rate in the system, which for the surface code remarkably is on the kind of scale of percents, then now as we increase the size of the lattice, we can in principle exponentially suppress the logical error rate. And this now starts to offer a realistic route to getting to extremely small error rates with noisy components. And I was not, around, why is this not? The clickers, oh, okay. So I was not around at the time, but it is at least my understanding that, back in the 90s, it was actually this theoretical breakthrough of quantum error correction that really allowed the field of quantum computing to take off. It showed that we can actually really build these devices in practice. And it is understood that although we've been learning a lot from kind of doing these, physical qubit algorithms and kind of learning what does quantum computation look like in the lab with really remarkable experiments, it's understood that eventually we're going to need to switch to performing our algorithms with error-corrected or logical qubits. And one big obstacle there is that quantum error correction is quite challenging. And the kind of optimistic estimates of what we would require for doing large-scale processing is something on the scale of millions of physical qubits in order to get down to large numbers of logical qubits operating at scale of 10 to the minus 10 logical error rate. And that's a lot of qubits. And that's further compounded by the fact that efficient classical control of quantum systems has so far been an outstanding challenge. While classical computers have gotten very good at doing efficient classical control, you can have something like order of 1,000 wires in order to control billions of bits in your system. Quantum computers have so far actually gone kind of in the opposite direction, where we're often building it in a way that it requires several wires per each qubit. And now to get to these really large scales is quite daunting. So this first big challenge is that of this wire problem, which although has not been a big obstacle to kind of small-scale physical qubit implementations, is a significant obstacle to that of large-scale error-corrected implementations. And another big obstacle is that once this logical qubit becomes delocalized, it becomes hard to accidentally manipulate, but it also becomes hard to intentionally manipulate. And for these reasons, this kind of large overheads and the complexity of operating on logical qubits have so far focused studies to the kind of scale of 1 or 2 or maybe 3 logical qubits and gates. And what I'll tell you about today is our approach toward solving these problems using a system that we call these reconfigurable neutral atom arrays. And what this system looks like is we have neutral rubidium atoms that are trapped inside of optical tweezers inside of a vacuum chamber. And these tweezers can be, for example, in multiple zones. And the qubit is stored inside of this long-lived hyperfine qubit. It's an electron spin, effectively, inside of this atom that has very long coherence times on the scale of seconds. And then to entangle atoms, we zap them with a laser beam that excites them to these so-called Rydberg states, these very high-lying orbital states that gets them to quickly interact and entangle. And then actually the coherence is so long in the system that we can move the qubits around in the middle of the quantum computation while preserving coherence. And the two really unique features that I'll tell you about in today's talk is that this approach gives us non-local connectivity, and it also gives us efficient and parallel classical control. And both of these, I think, are central to quantum error correction. So that's our approach. I want to take a little bit of time to acknowledge the kind of remarkable progress, both in theory and experiment, that has happened in the field over the past few decades. I mean, one, for ions have been talking about making shuttling-based processors for truly decades, and there's also these really beautiful recent experiments that people have been doing. It's actually from the superconducting qubit community that had this early experience with controlling moderately large systems that we learned about the importance of this wire problem. And actually, the cold atom community, the ultra cold atoms and the cold gas and optical lattice community is really responsible for a lot of the kind of early knowledge we've built in terms of how to control large-scale quantum systems based out of atoms. So kind of all of the work we're doing in today's talk will be heavily leveraging these various communities. And the clicker does not work super well. So, okay. So first I'll tell you about how do we program quantum circuits with neutral atoms. This will be the most experimental part of the talk. So I know this is primarily a theoretical audience, so I'll keep it high level, but also we're gonna get to more theoretical stuff later on. And then, is there any way we can make the clicker click more successfully? Should I point at something? So, and then I'll tell you about how we do error-corrected quantum processing with this device. So to start, this is how all of our experiments begin. We trap millions of cold, identical neutral rubidium atoms inside of our vacuum chamber using a magneto-optical trap. And what you should take away from this image, this is a very standard thing, this is not unique to our lab, is that there's, these cold and identical neutral atom qubits are essentially unlimited. So clearly number of qubits is not a problem, especially in this system. The problem, as I have mentioned, is that of efficient classical control. And that's baked into our experiment from the very beginning, where we can now trap and manipulate on the scale of 1,000+ neutral atoms in 2D lattices. And it's heavily leveraging this efficient classical control of qubit positions. And one kind of key optical tool that we use is that's known as a spatial light modulator. And what this does is we imprint a single laser beam onto the spatial light modulator, and then we control it. It's an LCD screen, essentially. It works very much like a computer monitor. And then it splits this single laser beam into many individual laser beams. And then we shine these laser beams inside of our vacuum chamber, and then here trap. We shine. Is there a, this is, oh, okay. Okay. So should I just point more directly, or what's the, I'll just, okay, all right. So, okay, so we can trap over 1,000 atoms in these tweezer arrays, and we stochastically load each tweezer with roughly 50% probability. But then we use another optical tool, which we call an acousto-optic deflector. And what this does is it uses 2 voltage waveforms, one X waveform and one Y waveform, that goes into this device. And just with these 2 voltage waveforms, we can in parallel reconfigure the system in large scales. So here we can make a 400 atom defect-free grid, and we can make any geometry in this way. So here we make a Mario, but we can make kind of many different types of configurations. And that's how we kind of lay out our processor. To entangle things and to do quantum mechanics, we use these so-called Rydberg atoms. And the ground state of our atom, the atom is quite small, but then what we can do is excite it with this laser pulse to this highly excited Rydberg state with principal quantum number ranging, for example, between 50 to 70. And when we zap 2 atoms with this laser pulse, what happens is that actually if both atoms are simultaneously in the Rydberg state, there's a very, very large van der Waals interaction. It can be on the scale of gigahertz. And actually what happens in practice is this means that 2 atoms cannot simultaneously get excited to the Rydberg state. There's this phenomenon of Rydberg blockade. And what this looks like is now if we put 2 atoms next to each other, both in the ground state and they're within a blockade radius, and we simultaneously try to excite them to the Rydberg state, then now what's going to happen is that they're going to both simultaneously try to go to the Rydberg state, but they won't be able to choose who gets to go, so they're going to go into an entangled superposition, Rydberg ground plus ground Rydberg. And we in our community have used this over the past few years to do a variety of different kind of quantum simulation experiments. Here kind of more in the analog or kind of Hamiltonian evolution setting, where we can, for example, arrange atoms into a Kagome lattice, just position these atoms, turn on this one global excitation laser, and that runs the Hamiltonian, and kind of we can study quantum dynamics from this. We can do phase transitions, non-equilibrium dynamics, combinatorial optimization, and it's really leveraging, again, efficient classical control. And now that we're studying digital systems, the big kind of question that we have is, okay, now we want to implement a quantum circuit, and it's decomposed into gates, and we want to be able to realize universal quantum computation, but we still really do not want to give up on this efficient classical control, even though there's more degrees of freedom in the system. And so again, just to recap, so now when we're going to do these digital experiments, we're actually going to store information inside of these long-lived hyperfine qubits, and we're only going to go to the Rydberg state just very briefly for generating entanglement. And a really big breakthrough in the field several years ago was that of the so-called Levine-Peakler CZ entangling gate, where the CZ gate, what you want to do is just map this 1-1 computational basis state back to itself with a -1 phase. And the kind of beautiful innovation here is that we can do this also with just global laser pulses. If we put 2 atoms next to each other, and then we just zap these atoms, and they go from this state 1 to Rydberg, and then they come back down, then all of the population comes back down to this hyperfine qubit. And due to this Rydberg blockade phenomenon, if both atoms are in 1, there's a slightly different Rabi frequency, and this actually causes the atoms to pick up a different phase on their trajectory. And just using this global pulse, we can now generate entangling gates. And so the really important aspect here is that we have global pulses, and we have this blockade phenomenon. And if 2 atoms are next to each other, they will do a CZ gate. And this now allows us to start programming quantum circuits where we put atoms next to each other, pulse this global laser, and if they're next to each other, they entangle. If they're not next to each other, they don't entangle. And the first quantum circuit that we did in this way was making a 1D cluster state where we put all of the atoms in plus, and then we do CZ gates on the links between the qubits. And here we have our two optical tweezer tools that we like, an SLM and an AOD. And what we do is we do one global pulse of our entangling laser. This entangles atoms on these first pairs. Then we just move half of the atoms in parallel. We do this by updating one voltage waveform that controls the x positions of all of these AOD atoms, pulse this global laser again, and just in these two steps, we make a 1D cluster state. And then we can probe this 1D cluster state by looking at these three body stabilizers, the ZXZ stabilizers, and benchmarks successful creation of the state here. And really, again, the key takeaway to remember about how do you program quantum circuits with neutral atoms is that the neutral atom tweezer community broadly has gotten very good recently at how do you control the positions of many atoms. And using this blockade phenomenon, now it maps the position onto the gate connectivity. And now we can just dynamically update the position in the middle of the circuit, and this now allows us to program complex quantum circuits by just programming the motion of atoms. Here, of course, you would like the stabilizers to be 1, and they're not because of decoherence. And in particular, the fidelity when we did these first experiments in 2022 was limited by our old 2-qubit gate fidelity of roughly 97.5%. We've made a variety of kind of experimental improvements since then, and particularly in 2023, toward doing high fidelity digital operation. And one aspect is that we now have roughly 99.5% fidelity 2-qubit gates on here 60 qubits in parallel. And we do this here with higher power lasers and kind of better cooling of our atoms, also this really nice pulse scheme from this Jindur and Pupillo group. And also note that there's also been some other really nice works with neutral atoms as well in Gateland. So that's how we do higher fidelity 2-qubit gates now. We also now have the ability to do fully programmable but also parallel single qubit gates. We use another AOD that we send our single qubit laser through. And what this allows us to do is actually, in principle, any arbitrary single qubit rotation on any atom that we want. But also what it allows us to do is with these AODs, we can make these rectangular grids. And then in just a single parallel step, we can, for example, do a Hadamard on half of our atoms. And for something like quantum error correction, this is a very powerful tool. And another aspect that we've developed is that of mid-circuit readout and feed-forward, where we can now, in the middle of the circuit, by moving our qubits away to a separate region, we can measure the qubits and then, in live while the circuit is running, decode the state of a logical qubit and then do a classically conditioned feed-forward operation. Okay, so that was the more experimental section. Now it's going to get more theoretical. And I'll tell you about now our explorations in doing quantum error correction with neutral atom devices. So when we did these first quantum circuits in our first work here, we made this toric code on a torus. And the torus we did kind of for fun and to show the fact that we have this non-local connectivity. And this is a movie of how exactly this circuit works. So again, we put these atoms next to each other, we pulse our global laser, and every time we put new atoms into new pairs, we pulse this global laser, and this causes them to entangle. Here the atoms move all the way around the system in order to make periodic boundary conditions and close the torus. And as we were doing these experiments, what was kind of clear was a pretty nice opportunity in the way that we're programming the circuit is that it's, again, just being simply programmed by specifying our SLM phase profile, again, like controlling a computer monitor, and our AOD waveform, which is these 2 voltage waveforms. And what this now allows us to do, these simple motion tools, give us now parallel control over many qubits with just order of 1 classical controls. And in particular, for quantum error correction, this is actually something that is really powerful. Because now, if we're going to start building error-corrected quantum devices and switching to doing logical algorithms, then imagine if you had, for example, an array of surface codes and you want to do error-corrected quantum processing. If you want to do a single qubit gate, a single qubit logical gate, what you don't have to go and do necessarily is a unique operation on each individual physical qubit of the block. All you need to do is effectively take 1 big beam and illuminate your 1 big logical qubit with this 1 big beam. And then in this way, you can do a transversal single qubit gate. With this transversal gate, we just do the same gate on every atom that makes up the logical block. But quite importantly, you can also do this for doing 2 qubit gates. So actually, we can just take these 2 logical qubit grids, interlace them with each other, pulse our 1 global entangling laser, and in this 1 single step, we can do pairwise entangling between all of the different physical qubits of the block and realize a transversal CNOT gate. And this now allows us to start exploring efficient and parallel computation, but with logical qubits, using the multiplexing of optics. And this is something that this transversal CNOT is really the kind of central point of this talk, so that's something that I'll just emphasize one more time, is that earlier I mentioned that by being delocalized, our logical qubit degree of freedom becomes hard to accidentally or intentionally manipulate. And now we have these 2 delocalized wave functions, and if we want to interact them through a boundary, for example, it's actually something that's quite noisy. But if we can just take these two logical degrees of freedom, put them right on top of each other, and pulsar one global laser, we can just get these 2 degrees of freedom to directly interact. And this is something that works at a much higher fidelity and is also much simpler. And there's kind of various benefits to this approach. And one is that it's inherently fault tolerant. And what fault tolerance means is that errors can't spread within the code block. It keeps the kind of errors from uncontrollably growing. And it's guaranteed here by the fact that it's a transversal gate. And this is a big simplification because it now doesn't mean, it means that you don't necessarily need to do something like D rounds of correction every time you do a logical gate, like it would be required for doing, for example, lattice surgery. And it also gives us, in a kind of large-scale processor, the ability to do long-range and direct connections between logical qubits that can have sometimes quite significant savings on the algorithmic level. And finally, from an experimentalist standpoint, it gives us this ability of efficient classical control. All of the physical qubits of this logical block, like in many error-corrected operations, not only this transversal C0, all of the physical qubits are just supposed to receive the exact same instruction, and we do this with one parallel pulse. And now we're using these kind of key concepts, really the central focus being parallel control of many logical qubits with only a few wires in order to be able to build our first generation error-corrected processor. And this processor is heavily leveraging transversal gates for our ability to kind of do these early fault-tolerant quantum computations. We have these multiple zones in our architecture. So we have a storage zone where, because of the very long coherence times in the system, the idle logical qubits can just be stored without having to constantly measure stabilizers and correct errors because the coherence is so long. If we want to entangle 2 logical qubits, we can just pick up 2 logical qubits on demand from the storage zone, move them into the entangling zone, and then just entangle them in the single parallel step. And then we also have this readout zone where we can move qubits in the middle of the circuit to the separated zone and then measure them and process real time without disturbing the active qubits in the circuit. And finally, as you know, this audience is very well aware, long-range connectivity gives you opportunities not only for doing, for example, transversal gates, but also broadly for studying many different types of exotic error-correcting codes, which we'll also study a bit here, but we're also interested in exploring even further in the future. So, okay, that's our logical processor, and kind of this, we'll start with the simplest example, which is just entangling 2 logical qubits and making a logical Bell state. And what this looks like here is that we make 2 surface codes, one in logical plus and one in logical 0. We do this by just doing a single round of stabilizer measurements here. And we measure the Z stabilizers in one lattice, the X stabilizers in the other lattice using an ancilla. And then we move these 2 logical qubits on top of each other and do this transversal C0. Here, this is for distance 3 codes. A really important quantum error correction property, as I had mentioned previously, is that you would really like to see operations improve with code distance. And there was this really beautiful experiment done by the Google group very recently, where they showed that they can actually suppress errors of the idling operation, or the coherence, by increasing the size of the lattice. And there's also this really nice work entangling 2 distance 2 surface codes from ions using lattice surgery. And here we study, going from distance 3 to distance 5 surface codes, and then also to distance 7, entangling them with this transversal C0 way. A really important asterisk in terms of what we're doing here is the state preparation is non-fault tolerant. It turns out to not affect the specific experiment that we're doing here, and it still allows us to probe this transversal C0, but we're only doing a single round of stabilizer measurement here. So, okay, so then we measure the logical qubits by looking at the XX and ZZ logical bases, and we see these, logical Bell state stabilizers. And in particular, what we see is that actually the logical Bell pair infidelity gets lower, or the errors improve, as we increase the size of the code. And so we can kind of see that we're doing a better job entangling logical qubits as we increase the size of our lattice. And again, just one more note here is that this shows we're beyond some kind of effective threshold of the system, but it's a little bit higher here due to the fact that we have nearby time boundaries in the decoding. And future work will try to do more and more rounds of stabilizer measurement in combination with more and more transversal C0 gates to see that we can actually increase the number, not only improve the fidelity of one gate, but actually increase the number of gates we can do. And another important aspect is how you do the decoding is actually very important. In particular, we use here this concept we call correlated decoding, which is very related to similar things that have been done in the literature, for example, those of space-time decoding, being led by a theorist in our group, Maddie. And it's essentially a simple observation here. When we do the decoding or inference process, we should take advantage of the fact that we know that errors between the 2 logical qubits should propagate in a deterministic way. And we do this by merging the decoding hypergraphs of the 2 logical qubits. Some kind of theoretical results is that one is that this allows us to take, theoretically, going from something like having to do D rounds per C0 every time we do a logical operation, now closer to, something on the order of 1 round per C0, which can have large savings in the algorithm. And it also works both for Cliffords and in some, it can also work for non-Cliffords. And a key observation here in doing these logical algorithm experiments, one of these kind of key observations we made early on is that once you're considering a logical algorithm, especially if it's like a Clifford circuit, then it doesn't really make sense to think about logical qubits separately. You should really think about it together as a whole, because then, especially for a Clifford circuit, it's just one big stabilizer state anyway. And this is kind of one way, this correlated decoding is one way that this emerges. So that's one way we're using our system. Another way is here we're doing kind of a more ion-style color code or Stein code experiment, where we make two distance 3 color codes, and then we do a non-fault tolerant encoding of them, but we use one of them as an ancillological flag. We do the transversal C0 by moving them on top of each other. And then by post-selecting on whether this flag saw an error or not, we can actually make this state preparation of the other logical qubit fault tolerant. And what we see is that if we do this non-fault tolerant state preparation only, the spam is quite bad. It's like 2% error of the logical qubit, which is worse than our physical atom. But if we use this transversal C0 and post-select on our flag, then it's fault tolerant, and now the fidelity improves quite significantly to the scale of roughly 3 nines. And to the best of my knowledge, this is worse only than the quantinuum group, which is also quite close to in terms of logical fidelity initialization. So, some bullet points. So error correction here we're using to improve the fidelity of our state initialization. And also we're heavily leveraging, again, this transport-based C0 for effective logical operations. And importantly, we never do things on single physical qubits at a time. We also try as much as possible to never do things on single logical qubits at a time. And this data here is averaged over 10 total logical qubits or 5 logical pairs. And once we make these logical qubits, we can start exploring algorithms between them and start to explore the subtleties of that. And here we're doing one of the first things that you would do anytime you make a new type of quantum device is make a GHZ state. So we have these 10 logical qubits. We use 5 of them as ancillas to check for errors on the other ones and do fault tolerant initialization. We take these ancilla logical qubits, drop them off in our storage zone where they're safe from errors, and then we make a 4-qubit GHZ state out of our 5 logical qubits just because it was easier to do tomography on the 4. And then we measure them with single qubit Clifford rotations. One of the challenges of doing logical qubits is you can't do continuous angles. So we can't do, for example, parity oscillation. So we actually use this direct fidelity estimation technique in order to extract the fidelity of the state. And we see that we can prepare, by using our fault tolerant initialization, we can prepare a genuine multipartite entangled GHZ state. If we do error detection, where error detection is post-selecting on the stabilizers of this computation logical qubit, then the fidelity improves to roughly 99.8% for this GHZ state, but at the cost of post-selection overhead. And we can also start to do other things that we like to do with physical qubits, but now start doing them with logical qubits and kind of explore the different subtleties. So here we're doing, for example, logical tomography of our logical 4-qubit GHZ state density matrix, and can start to really explore these kind of early fault-tolerant quantum computations. And here's a movie of what this GHZ state circuit looks like. So we have 10 blocks. These are 10 blocks of 7 qubits, and they make up these 10 distance 3 color codes. In the first 3 steps, so 1, 2, 3, we do the encoding of the color codes. Then we pick up the top 5 color codes and use them as flags, doing a transversal C0 in parallel. We drop them off in the storage zone here, and then we pick up these 2 logical qubits and then kind of just slide them around the system and do these transversal C0s in order to program this GHZ state circuit. So here you can see we made a GHZ state, but we can do any Clifford circuit that we want in this way with these color codes. And another thing that you can see is that this approach pretty directly scales. So we can use this zoned approach where here, for example, what I just showed you, you make 70 physical qubits encoding 10 color codes, but then we can just directly scale it, and we can go to, and for example, make 40 of these distance 3 color codes. And the way we do this is we just, entangle qubits, drop them off in storage where their coherence is long-lived, and then we pick up more qubits, do all these operations again, drop them off. And it's really heavily inspired from these classical architectures where you have, for example, RAM, you take information from your RAM, you process on it, you put it back in RAM, and kind of really starting to explore this, architectural level analysis of how do we, do efficient classical control of these large-scale systems. And that's how we're able to make, for example, here, these 40 distance 3 color codes. So that's one aspect of our zoned processor. Another aspect is that of doing this mid-circuit readout and feed forward. And here, this kind of test experiment that we do is we make a 3-qubit GHZ state, we measure the middle qubit, and we do a kind of entanglement teleportation where we get the 2 outer qubits to entangle, to be entangled by doing a classically conditioned feed forward S-gate. So this is what this looks like. So we pick up, these are real atom movies, by the way, if maybe I didn't already clarify. So these are real pictures of our experiment. And then we did these 2 transversal C0s. We move them into the readout zone, measure it, decode live, and then do these logical S-gates on our logical qubits. And this, projects us either into the phi plus or phi minus Bell state, but then we correct by doing this S. And what we see here is that we, indeed, if we don't do this feed forward process, then the XX and YY parities are 0, excuse me. But if we do the feed forward, then we do indeed recover this Bell state, and it's limited just by the fidelity of the underlying 3-qubit GAG state. If we instead just post-select on the middle logical qubit, always having been in the right state, but we don't do any mid-circuit readout or feed forward, then we get the same fidelity as if we do the feed forward step. So it kind of is a good test. Okay, so those are the various aspects of our zone processor. But another kind of really important aspect now that I'll tell you about for the remainder of the talk is the following. So once we're starting to build these logical processors in the lab, you realize that, especially because of this flexible architecture, there's quite a lot of options. And there's options both in the error correcting code, the algorithm. There's also kind of native hardware capabilities. And a really central focus here is that of co-design. We want to really find specific error correcting codes that will work for specific algorithms that are also specifically tailored to that, the capabilities of our hardware. And in entering this era of doing early fault-tolerant quantum computations, where we're starting to really see how does quantum computation with logical qubits look like, and we're searching for as many kind of breakthroughs and as many factors of 10 as possible, I think this is going to be really a very central focus, as tailoring algorithms and error correcting codes to each other. And a really important aspect here, and something I've kind of swept under the rug so far, is a big challenge with doing error-corrected quantum computation, is that error-correcting codes, for intrinsic reasons, can only have a discrete gate set available. And for these 2D surface code and color codes that we talked about here, we can actually only do the Clifford group, H, S, and C not easily, and we cannot easily do non-Cliffords, T or CCZ. At least we can't do them transversely, and I would say kind of, yeah, okay, I would call it not easy. And we need a non-Clifford gate in order to complete a universal gate set, but it's actually even worse than that, because not only do we need a non-Clifford gate like T or CCZ to complete a universal gate set, we actually need a non-Clifford gate to do any non-trivial quantum computation. And this you can understand just by this Gottesman-Nil theorem, where, for example, if I have a stabilizer, like a logical stabilizer of my state, and it passes through 2 CZs, I can just track how this operator spreads through this Clifford circuit. If there's a CCZ gate, however, and now I feed in this operator like XII, and it hits the CCZ, now it goes into a superposition of different operators, and I have 4 times more operators to track, and I'm going to exponentially increase the number of operators I need to track as I do more and more non-Clifford gates. And state-of-the-art kind of Clifford plus T simulators, to the best of my knowledge, I would be very interested in being corrected if I'm wrong, can handle roughly 64 T gates or 16 CCZs. So it's something that, kind of leveraging the kind of low magic or low non-Clifford, non-Cliffordness of the system kind of stops working well at this scale. So what we're going to study here is if we can find specific algorithms that we can do very well with specific types of error correcting codes. And in particular here, one thing that we'll use is the long-range connectivity in our system in order to make 3D codes. And these 3D codes, it turns out they lose a transversal Hadamard, but they do gain, in certain cases, transversal non-Cliffords like the transversal CCZ. And in particular, we're using this 832 code, which means 8 physical qubits, 3 logical qubits, and it's distance 2 in one basis, distance 4 in the other. This 832 code has many really interesting properties. It encodes these 3 logical qubits that are given by this X faces and Z strings on these 3 different faces and strings. And importantly, it has this really rich transversal gate set. It allows you to do a logical CCZ just by doing single physical qubit rotations, like T's. And this sounds like cheating. We're going to generate logical entanglement just by doing single qubit rotations, which is very simple. But the key is that we pay back our entanglement credit every time we do transversal C-naughts between different 832 codes, because these are CSS codes, and so they also have a transversal C-naught. And so we have this CCZ and also pairwise CZs within the blocks. We have the C-naughts between the blocks, and we can also do a permutation-based C-naught by just physically moving the qubits around in the block. And so here we're going to study kind of how can we just generate a lot of entanglement and a lot of magic. It's important to know that it can be, with 3D codes, can be very straightforwardly made universal simply by doing measurement and feed forward, like I showed earlier in the talk, to teleport in a Hadamard. So universality, especially with these 3D codes, is really not such a key problem. The key problem is more the distance cubed scaling. So then we make 16 of these 832 logical blocks corresponding to these 48 small logical qubits, and we start to explore algorithms with them. And what this looks like here is we're going to do algorithms of the following nature, where we put logical qubits all in logical plus, and now we do parallel CCZ and CZ gates within the blocks, and then we do transversal CNOTs between blocks. So this circuit here is our logical circuit. There's 48 lines corresponding to the 48 logical qubits that we're doing, and 228 logical 2-qubit gates and 48 logical CCZs. Kind of just for fun, but also because it makes a really good scrambler, is we're entangling all of these things on hypercubes. So Michael is here, he's a close collaborator, and he loves the hypercubes too. So you can definitely ask Michael a bunch of questions about the hypercubes. So yeah, we entangle all these logical qubits on these hypercubes, these 4-dimensional hypercubes. Each logical qubit is a 3-dimensional cube, so the physical connectivity is that of a 7-dimensional cube. And it turns out that this maps to doing IQP circuits, it turns out. And IQP circuits, or instantaneous quantum polynomial circuits, are actually a very well-studied type of supremacy circuit that we can implement now with our logical qubits. There's also this really nice work that's also being presented here. And they're kind of amazing theorists here understood this connection between to these IQP circuits. It's actually very rich. You should talk to Michael about it. Okay, and now we can study these IQP circuits and start to do different types of things like sampling, for example. And sampling, what this looks like is we do a complex quantum circuit, and then we make projective measurements and compare the output distribution to that of what we were expecting. And then we quantify this sampling score by looking at this XEB score, this cross-entropy benchmark, which is just a way of saying we're doing a weighted sum of the expected probability distribution with that of our observed probability distribution and normalizing it from 0 to 1. Okay, and it turns out actually that XEB has this really interesting connection to fidelity for IQP circuits. It's actually a pretty good fidelity proxy for IQP circuits in particular. So, okay, this is what our experimental data then looks like. So if we don't do any error detection, so here in this experiment, we're doing post-selection and throwing away data by utilizing our stabilizers to do an error detection approach, because it's only distance 2, so we can't do correction, at least for this experiment. We'll do correction in a little bit. Okay, and what we see is that this kind of theoretical distribution in the back has these kind of little tiny peaks, and the raw distribution is starting to overlap with them and show some agreement. But as we increase the amount of error detection that we do, we start to see better and better overlap between the measured logical outcomes with that of the theoretical distribution. In particular, if we quantify it with this, XEB score, then what we see is that as we throw away more and more of our data, quantified here by our accepted fraction, again using these stabilizers for doing error detection, our XEB score continues to improve and gets to a value which is quite high for 12 logical qubits and this kind of complexity of circuit of roughly 0.7 here. And I want to just zoom in on the data a little bit more closely. I still stare at this data every once in a while and kind of wonder why does it look as good as it does. And I want to just kind of zoom in a little bit and kind of give a sense. So here again, we're looking at our logical sampling outcomes. There's 12 logical qubits here, so 2 to the 12 possibilities. And as we zoom in further and further, what we see is that, sorry, I'm doing my best. So what we see is that we're zooming in here smaller and smaller. Just track the red arrow. You can see kind of these tiny, teeny little features in this top plot here. These 2 tall peaks at the bottom. You can see the overlap between the experimental distribution with our logical qubits with that of the expected theoretical distribution. And this is something that we have not seen before with physical qubits. And I think something that's quite amazing here and something that's quite unique to logical qubits is that logical qubits digitalize your errors. And that's something that I think we kind of are starting to see from these early error correction experiments is, yeah, the fidelity is not perfect here. It's not perfectly overlapping with the distribution, but the shape overlaps very well. And you can see that even down at this 10 to the minus 4 level, there are kind of tiny little ripples in the theoretical distribution get reproduced by our experimental distribution. And this is, again, not something that we see with our physical qubits. So that's kind of one way of looking at the data. Now, so that was all 12 logical qubits. Now we'll scale to 48 logical qubits and these hundreds of logical entangling gates. And what we're plotting here are different system sizes and our error detection accepted fraction. And we see in all cases that we get a finite XEB, which corresponds here, thank you so much, which corresponds here to doing successful sampling. And we see that this XEB score improves with doing increased error detection, showing the benefits of using logical qubits here. The post-selected XCB that we get here is, to the best of our knowledge, roughly a factor of 10 higher than previous physical qubit implementations at a kind of comparable scale, but at the cost of measurement time. So there's trade-offs. You can use this problem. Sampling is a kind of problem where you actually cannot do anything to improve your score. So actually, the fact that you can wait longer and get a higher score is actually a very interesting trade-off, and it's kind of an interesting application of using error correction for near-term algorithms. It's also significantly higher than in our system when we tried doing this algorithms with physical qubits. This here plotted on the right is an upper bound of how good our physical qubit can be, and then the error detection is quite a bit higher than that. And we actually had to intentionally structure, so these are quite complex circuits. We had to actually, so this is not, we're not claiming anything about quantum supremacy, although it's quite close within reach. Simulating each bit string still actually takes several seconds here on a classical device, but we're actually intentionally structured our circuit in a way that we can simulate it. But it's actually kind of already in a pretty large regime for kind of doing near-term tests of quantum supremacy with error-corrected qubits. Okay, so and here is a movie of how exactly this quantum circuit looks like. So we entangled these local blocks into these cubes. So that makes this 832 cubes. And now we entangle them on these higher and higher kind of dimensional structures in order to make these higher and higher dimensional hypercubes. We run out of space here, so we take these logical qubits, we drop them off in the storage zone, we pick up new physical qubits, run the process all over again. All that time, these qubits are in the storage zone preserving coherence. Okay, and then right here at the very end, we then take this first group and then do a gate with the second group. And this is just the way that we chose to structure this circuit, but you can kind of get a sense of the flexibility of the system. And we can do other things with our logical qubits that we like to do. And one of that we like to do as physicists, and one of them is actually also doing these 2-copy measurements. We do scrambling circuits on 2 copies of our 12 logical qubits, and then we actually measure them in the Bell basis, and we can extract a lot of really interesting information. We can extract the entanglement entropy, for example. We can extract the absolute values of all 4 to the n poly strings, which is really interesting. And this is fully compatible with doing these error-corrected circuits. And here what we see is we're doing these kind of scrambling circuits. These hypercubes actually turn out they're fast scramblers, so it's related to some interesting physics there. And we see this kind of characteristic page curve where especially when we apply our full error detection, the entanglement goes up, and then once it gets to half the system for this scrambled state, it starts to go down. It's this kind of characteristic page curve triangle. And this is quite a bit cleaner of page curve dynamics and kind of entanglement dynamics than we've been able to see before with using physical qubits. And it kind of shows us that we can already in these early generation devices start to use logical qubits for interesting physics and quantum information applications. I think I'm running out of time, so I'll just breeze through this, but we also can use this 2-copy data, for example, to measure the amount of magic in the system. So we measured the amount of logical magic generated as a function of the number of logical CCZ gates. We can also use it to extract all of the Pauli expectation values. There's 5 discrete values here. But actually, quite interestingly, we can do this sliding scale error detection, which reduces our purity and reduces our Pauli string expectation value, and then kind of do like an intrinsic zero noise extrapolation all using just this one data set. So it's kind of, there's a pretty rich things to start exploring with these encoded qubits. Okay, so now to just summarize my talk. So we're exploring this quantum information processing with logical qubits. We see that quantum operations, like the transversal gate, can improve as we increase the size of the code. We make surface codes as large as distance 7. We start to do fault-tolerant algorithms and characterize our zone processor and start to study these kind of complex scrambling circuits here with these small 3-dimensional codes. So just kind of a flavor of all the different things that we can do here. And so the kind of natural question is, what did we learn and where do we go from here? So in terms of some lessons from our first generation logical processor, I think the really central one, especially as an experimentalist, that I would really want for you all to take away is that the control over single logical qubits as the fundamental units in the processor dramatically reduces the costs of building a logical processor. And if you would come into our lab, this is really like a university lab experiment, built and run by, a few grad students and postdocs. Also in collaboration with some other institutions, but kind of really just like it's a university lab experiment in a basement. And the reason we can do all these complex circuits is because of parallel control over logical qubits. Here, when we're doing our GHG state, this is what you would see when you came into our lab. We have these 10 lines here. These are the 10 logical qubits. And we think about how do we program a transversal CZ or transversal C0 between these 2 logical qubits. We just move these 2 logical qubits together, pulse this one global laser, and do this one logical gate in a single step. And so that's a really central point of building, these error-corrected processors that I really cannot see going away. This is parallel control. Another really interesting aspect that we start to see is that it doesn't really make sense at this scale to consider individual logical qubits. It really makes more sense to consider algorithms as a whole. It's actually quite interestingly related to this kind of space-time decoding concept. Another type of thing that we learned is that logical qubits are not literally qubits. They're many-body systems. They're quite subtle in the way that they behave. They don't always behave in exactly the way you expect. Sometimes there's kind of comes with bummers. Like, for example, the Bell state fidelity is not just equal to something like a spam times the gate fidelity. These notions are sometimes not so well defined. But on the flip side, we actually were pretty pleasantly surprised by what this looks like, this kind of digitalized errors, that coherent logical errors are suppressed in the system. It's kind of a unique opportunity with logical qubits. And I think that there's already kind of some genuine examples where we can use these logical qubits and these early generation devices to outperform physical qubits at interesting problems. And of course, a really big challenge here is this discrete gate set. The discrete gate set is a curse. But actually, if you flip that around, it can be a blessing. Because, for example, if you find a specific algorithm that lies within this kind of simple set of discrete gates that you can do, then it's one of the few unitary evolutions your logical qubits can even do. So it's actually something that it can realize really precisely. And I think there's going to be many more opportunities here for doing these early generation logical algorithms. So that's kind of lessons from our first generation, what I would call like early generation logical experiments. I think something that's a quite unique opportunity for neutral atoms is that of kind of going toward these medium scale error-corrected devices, as we would call it. And one really important next step here is here we're doing algorithms with logical qubits. Now what we really need to do is algorithms where we also pump out entropy in one way or another in the middle of the circuit and actually extend the depth of the algorithm that we can do. So that's an important next step we're working toward. Another thing is that the kind of existing techniques, just again using parallel control, can pretty readily be scaled to the scale of roughly 10,000 atoms, and we think that we can get to the scale of roughly 0.1% errors in the quite near term in terms of our 2-qubit gate fidelity, for example. Another really important aspect is that we need to be able to continuously reload our atoms. Atoms leave the system at some rate, and we need to be able to continuously reload them. And I really just want to highlight here, this neutral atom community, I think, is a pretty special place. And we're taking a pretty collaborative approach. And there's many quite amazing things people are working on across the community. To just name a few, there's kind of different types of clever optical networking. There's erasure. There's actually a really interesting erasure poster here from the Puri group that you should go see. And exploring different atomic species. I think there's really unique kind of collaborative opportunities that we're working on here. And all of these, I think, in the coming years are going to coalesce to being able to make kind of medium-scale error-corrected devices. There will be challenges, but it seems like we do have a relatively clear path to making something on the scale of 100 error-corrected qubits that can do something like 1 million logical gates. And this medium-scale error-corrected device might not solve big problems necessarily, at least yet. But I think it will be a really new scientific tool. It will almost be kind of conceptually different from being able to do the kind of types of quantum computations we're doing now. It's a quantum system that's not limited by depth. And I think two really interesting theory questions that I want to just kind of put out there is that what types of algorithms should one study if you have something like 100 logical qubits and 1 million logical gates? I think it's actually a pretty non-trivial question. And similar to this 832 circuits that we did here, how do we structure these algorithms for efficient quantum error correction implementation, kind of clever co-design in order to make leverage of these systems? And this is going to be my last slide. That's this kind of medium-scale error-corrected devices. But we're also thinking beyond, how to get to these really large-scale logical processors that can, for example, be used to solve, large-scale chemistry problems or, other kind of interesting problems. The kind of optimistic estimates here, is that we still need things on the scale of, millions of physical qubits operating with, 10 to the minus 10 error rate with, coherence times on the scale of days. And my honest assessment of this is that it's actually still, quite daunting. I mean, we definitely have ideas, and we're working on these things. So. And we're working on these things. For example, there's LDPC codes. There's actually going to be an LDPC code talk from our collaboration that you can go see today. There's different ways that you can maybe do power efficient trapping. We're also considering whether you can connect different photonic modules. And I think that we definitely have ideas here in terms of how to get to this large scale. But the reason I want to emphasize is that it's not completely solved, is that we should really at this scale be pursuing all possible breakthroughs that we can get, both from the hardware but also from the code and algorithm design, and kind of get as many factors of 5 or 10 that we can. And at least in my personal belief, the experimentation that we do in the coming years with these early and medium generation error-corrected devices will likely reshape the way that we think these large-scale logical qubit devices should be built. Thank you. That's the end of my talk. I'd like to thank my amazing colleagues.
Thank you so much, Dolev, for that amazing talk. Just to clarify, how many papers did you write last year?
I think.
Is that all in one paper?
Oh yeah, so there's the high fidelity gates paper, and then the logical processor paper is one paper.
I'm like, there's way more in there than, I mean, gosh, I'm feeling really bad about my PhD all of a sudden. You're giving us all imposter syndrome.
You're being very sweet.
So we have time for some questions. How is this going to work, by the way?
Hello.
Do we have mic runners?
Hello.
There's a talk. There's a question over here.
Yes, sir. Hello. Thank you for the talk. You said you're doing a post-selection. If I understood correctly, you said you're doing post-selection because you cannot correct the errors on the fly. And also in the end, you kind of mentioned that you're trying to make the post-selection more efficient. Not the error correction more efficient, sorry. So I was wondering how much of the data are you throwing away in the post-selection, and how much are you keeping it?
So I'm not going to scroll all the way back to the slide, but okay, let me clarify just a few things. So one is that we did kind of 3 different types of experiments. There's these 832 experiments. There's the color code, surface code experiment, and also the 2D color code experiments. In the surface code and 2D color code, we're just doing correction. So it's kind of standard. And for the 832 experiments, because when we're measuring it in the distance 2 bases, we can only do post-selection. Actually, when we measure it in the distance 4 bases, we also do some correction as well. But yeah, okay, so I won't scroll all the way back there. But with our 48 logical qubits, we start to throw out as much as 999 out of 1,000 samples. This is not a scalable approach, right? I mean, it's an interesting approach for early generation things where you can kind of start to really get a sense. And also for sampling, I mean, we get a higher sampling score than we can do in other ways. So, we can solve certain problems better using this technique. It's clearly not something that allows you to solve, really large scale problems. It's maybe, yeah, so yeah. But we can, for example, make a distance 3 version of this, 3D code and then kind of do algorithms in this way. We would just then need to use more qubits, but that's definitely the direction things are going.
There's a talk over here. Oh, or that one, yeah.
Thanks for the talk, that was great. Just a question about the errors during motion. So you can excite motional degrees of freedom, which could affect future gates.
Yeah.
And also, if you're thinking about long depth circuits, then you might have to refresh them, but then you have trade-off with allocation of power and how many you can reconfigure and refresh. So how do you model those errors?
Oh, great. So yeah, so in terms of motion, so I mean, when we do free space motion, if we're just careful with our dynamical decoupling, there's really no additional dephasing from the motion. So there's this kind of 2-second coherence time. The typical movement time is like 200 microseconds, so it's kind of 10 to the minus 4 scale. Yeah, so I mean, the free space motion works very well. One of the things that we did here that worked slightly less well is we transfer atoms between different tweezers, and that was working at a fidelity that was a little bit better than 99.9% in terms of both dephasing and loss, but we would like to make that also a fidelity of 1. So these are things we can improve. When you do very deep algorithms, the atoms will get hot and the atoms will get lost eventually. It's not really from the motion, it's actually more from the 2-qubit gate. Every time we do a 2-qubit gate, sometimes we accidentally leave population in the Rydberg state. When we turn the tweezer back on, this atom disappears. So that causes loss in our system. There is no way we can do 10 billion gates without losing an atom. And so we need to be able to continuously reload them. Yeah.
There's a question here.
Thank you very much for the nice talk. I wanted to ask about these transversal gates, which I like so much, that you can, with one laser beam, kind of do operations on many atoms. Can you also use kind of vector beams for that, so that you could kind of couple to the individual atoms differently using the polarization that varies over transversal plane, and then implement different pulses in that way? Have you thought about it?
Oh, very interesting. So, I mean, definitely could consider doing some types of local variations in that way. I think it's a very interesting idea. For doing the transversal gate, actually, we want all of the instructions to be the same. So at least for the 2-qubit gate here, it's just this global thing. But something that's actually a little bit more similar to what you're describing is that we also have fully programmable single qubit gates. And that we do with these AODs that we can dynamically program, and maybe a more efficient way could be to use this polarization control or something. But I think our current approach works quite well. Yeah. great question.
Yeah, there's a question here and then.
You said you've been seeing physical improvements over the years, and you're expecting to the physical errors to improve further in the future.
Yeah.
Where the improvements are coming from?
Yeah, primarily, I guess, spending more time on the problem. But I mean, so really, there was really a lot of very pioneering work done in the field with the Rydberg atoms over, decades that kind of started to iron out some of the basic things. But actually, before 2019, the state-of-the-art Rydberg gate fidelities were actually below 80%. So that was when I started my PhD. This Levine-Pichler gate took it to 97.5%, and it was really this global control and this kind of simple pulses that were really important, as some of the aspect. In this recent work, I mean, it's almost a trivial change. It sounds almost like a trivial change, but there's these, two theorists, Gendure and Popio, and also there's this nice work from the Buchler group. They just proposed doing a single pulse. It should only be a little bit faster, but it turns out that actually due to some Rydberg physics reasons, it seems, or some miscalibration reasons, that actually allowed us to go from like 97.5 to like 99.3. And then 99.3 and above, to like 99.55 roughly, was, higher laser power, colder atoms. And I think we, now at our current status, we have like a pretty good recipe. I mean, all of our errors are reproduced by atomic physics error modeling, essentially, at least down to the 0.1% level. So I think we're feeling pretty confident that essentially by increasing laser power, we should be able to get to kind of roughly 3 nines fidelity. I do not think we have an idea in terms of how we would get to 4 nines or something like that. And again, I would also really highlight the other kind of groups that are working on these like, 2-qubit gates, for example, and they have other interesting, challenges, but also opportunities. So I think 99.5 is definitely not a hard cap. And it'll improve very soon. I highly expect. Yeah. Mm-hmm.
Thank you.
So I think Graham has a question.
I have 2 questions. Can I ask, first, what are the prospects for doing a CNOT gate with improved fidelity over your bare CNOT gates?
Uh-huh.
And the second question is, what's the slow step in all of this? And what's the implied logical
Clock speed.
Clock speed.
Yeah. Okay, I was waiting for the clock speed question. So here we were actually primarily, to make like a logical gate better than a physical gate, it depends almost on your definition. It definitely depends on the code that you're using. So for the surface code, we were not, pushing toward that. We were just trying to see that we get, improved performance with code distance. We actually tied our Bell state, our logical Bell state, with our physical Bell. So our best physical Bell state is 98%. We tied that with logical qubits. It's not in our paper, by using color codes. So it's just slightly different and using some flags that kind of improve things. So I think being beyond break even is really like, almost, if we would have focused on it more and tailored the experiment to it, as opposed to being, for example, better than threshold, then I think that's something that we could have quite easily seen. Of course, it gets easier and easier the more you improve fidelities in the system, but I don't really see that as kind of like a hard, cap or milestone for us. Okay, clock speed. So everything in the system is kind of, the gates are like hundreds of nanoseconds. There's nothing fundamental there. The motion and the readout currently are on the scale of like 200 microseconds. The readout is like 500 microseconds, but it can be made quite a bit faster. And it's true if you want to do 1 trillion logical gates, you really want them to be fast. I think I don't disagree with that at all. At this kind of medium scale error-corrected devices, if we do nothing different than what we're doing now, we should be able to do 1 million logical gates on the, also with parallelism on the scale of, 1 to 10 seconds. That's how long these circuits will take. And that's when, at least, other people are working on this now. At least as my perspective, an experimentalist, you can't convince me right now to make the thing faster because it doesn't limit anything. But at that scale, you're going to have the PhD student sitting in front of their experiment frustrated that it's running so slow. And then that's when we're going to start saving factors of 10, in terms of the speed. Yeah. But the other thing is that I just want to quickly comment on there is also the fact that this, long-range connectivity also gives quite a lot of savings in this kind of clock speed. I mean, it save a factor of D pretty directly. Also in kind of large-scale algorithms, the fact that any 2 logical qubits can connect also can have big savings. Yep.
Oh, okay, we have time for one last question.
I have a question.
Hang on, I already promised this guy. Sorry. We have time for one last question.
Hi, thanks very much. So my question is about geometric locality. As the number of qubits grows, it seems like because the physical qubits are in a 2D array, the transit time from one edge of this array to the other will grow with n. So when I think about depth complexity of the circuit I'm implementing, should I think of these circuits as geometrically local, or do we think of long-range swap gates as O of 1 time?
I would call it O of 1 time. So one is actually, so the time to move scales as like square root of the distance that you move, so it actually is a little bit more favorable than that. But the other thing is that we're not really super limited by the dephasing from the motion. So I mean, at least currently in kind of trying to build these devices, the thing that's still limiting is the 2-qubit gate. So I mean, I think a pretty good mental model right now is that there's no cost from long-range connectivity. The cost is from no parallelism. When you do things in parallel, it's like a single step. It's very smooth and it's also just very efficient. If you have to do like a really strange type of permutation in the system that's very not parallel, that's the cost. So long-range connectivity, cheap. Doing things not in parallel, expensive.
Okay, I feel bad, so I'm going to let you ask one. This is the actual final question.
Quick question. So nice talk. So if I understand correctly, every neutral atom corresponds to a physical qubits. And how many physical qubits or neutral atoms do you need for a logical qubit? Is it a fixed number, or it depends on the complexity of the magic state or you want to achieve? And how can you achieve this error correction to other technologies like the superconducting and that you showed in the beginning of your talk?
Right, yeah, fantastic. So, okay, 2 very good questions there to end on. So, so one is that we make a variety of different logical qubits. And logical qubit, people will argue on the definition, right? So, I mean, we make surface codes, 2D color codes, and these 832 codes. So the 832 is kind of a 3 to 8, or 8 to 3 encoding, and then the surface code, we use as many as 49 data qubits, also with the ancillas, to make, 1 surface code. So, in kind of going toward large-scale processors, I mean, if you imagine surface codes, maybe you need, hundreds of atoms to get to the relevant errors, but maybe we would like to be more clever, right? And then maybe kind of depending on what you do, I mean, either with LDPC codes or with, kind of using clever codes to kind of cut down on the non-Cliffords, I think it's not exactly, there's not a fixed number, but I think in the large scale, I would have a number in my mind of, 10 to several hundred, somewhere in that range, and the 10 would be if we're very clever. So so that's the first question, and then the other question: what should we learn from this from the other systems? Because we learned so much from them, right? And I think the main thing I can never see going away is parallel control. Like if you have 1 million qubits in the system and 500,000 of them are supposed to do the exact same operation, then you need to deliver that in parallel. If you're doing that in 500,000 separate ways, you're going to make it way more challenging than it needs to be.
All right, let's thank Dolev again for a wonderful talk.